from a domain that is normally developing on fairly long time scales and very conservative. It's kind of just mind-blowing to see the speed of developments that within 3 years we're basically going from a good idea to an operational system. And there doesn't seem to be a limit. So I think we will still see this pace of developments going on for the next 2 to 3 years. I'm Peter Dueben. I'm the head of the Earth System Modeling section at ECMWF. So we're building basically the next generation of models that are then used for numerical weather predictions on the global scale. I was there from the very beginning. So actually we wrote a paper in 2018, which I think is the first paper that ever trains a global machine learning model from era 5. Just to see develop and the pace of development is just incredible, right? The machine learning model development itself for numerical weather prediction started from the atmosphere only. So a model like AIFS, for example, would normally historically only represent the atmosphere really in 3 dimensions. But this is changing now. So more and more model components are actually added to the model configuration basically. We kind of adding different components like land surface, waves, snow and sea ice, and the ocean to the AIFS and make a real system model from it. And by doing this, we basically then in the end will also be able to perform much longer term time simulations basically. There's a caveat though, which is in a physical model, you normally assume that by adding components and making them realistic, you basically also improve the holistic picture of the Earth system in your model, and then you also have better predictions. And for machine learning model, that's not so clear because these components are normally already in the training data set. So even though you're not explicitly representing the ocean, you actually implicitly do represent the ocean. And these are really interesting science questions that we need to look into and then also explore. The final point I want to make is also you also building trust. So by making the model more realistic and adding more components to it, and really also understanding the limits of what you can represent, for example, for the deep ocean, for example, you're also building trust in the machine learning forecast system. The first generation of machine learning models was deterministic in the sense that they basically try to predict the most likely scenario of the future. And now the next generation is already able to do probabilistic predictions. So they can basically predict uncertainties as well with the predictions. And they normally do this via ensembles. If you train for an ensemble, you're actually able to preserve very sharp gradients, and therefore by going to the ensemble, you actually also improve the realism of the individual ensemble member, basically. That's fantastic news for us. It's also, the machine learning models are very good at doing this. And there's another component to it, which is you're also building so-called generative machine learning tools now. So by being able to represent uncertainties, you also build tools that are actually able to generate features on the small scales to really build gradients. So there's, for example, an application we call downscaling, where you come from very coarse resolution global models and then you downscale to a finer resolution grid. So you can actually think about new ways of working with those models. You can, for example, go down a route where you basically just fill in gaps, or you can also ask the machine learning model, for example, to generate fully complex 3-dimensional weather regimes. There's, for example, tools like cBottle from NVIDIA, or a project called Weather Generator, where we build generative machine learning tools. And doing this, we will be able in the future to just say okay, I want to actually have a realistic tropical cyclone in the year 2030 over the Caribbean, and I want to have a distribution for it in a lot of different ways of how this tropical cyclone could look like. And the machine learning model will be able to generate these things. And you will also be able to play around with it. So for example, just add more temperature to the surface fields and play with what if scenarios. You can do all of this with a generative machine learning tool. So there's a fantastic new world basically lying in front of us that we can explore. In the first place, we already see that we now will be able to deliver better weather predictions with machine learning models in terms of forecast scores. So you can think about the future where you have a 4-kilometer global machine learning model, for example, running on a single compute node. And this will really also deliver a lot of interactivity. So you will be able to actually explore a huge amount of data sets and the information from the data sets with machine learning in a much more interactive way and a much more basically real-time and real-time way that you can really look into the fields how they're developing. So there are huge opportunities ahead. One other thing that is still to be considered is how much we can actually train directly from observations. So if we can manage to get real good weather forecasts as well, just directly from observations. And we can also do data simulation with the models. That will be another step in the quality. And then I think also this kind of new visualization features that we have and stuff like this, also large language models for coding itself. So there's a huge imprint of machine learning and how this will basically change how we do our system modeling in the future. There's one downside though. You always have to be careful that you don't use the machine learning model beyond what it's actually capable of doing. So the training data will give you a framework, what the model can and can't know, for example, regarding climate change. And if you go beyond that framework, you're actually extrapolating into an unknown future. Obviously, we're also assuming that the Earth is kind of developing as it used to be, right? But imagine there's, for example, a volcanic eruption somewhere, and it will change the atmospheric dynamics, and the machine learning model will not necessarily know what it actually is. Or just assume that kind of there's a huge problem with the observation data coming in, for example. This will also change the quality of the model, and we may not even know what to do then. So I think we still will need physical model in the back pocket, basically, and still have them and run them. The upcoming generation of systems modelers or weather and climate scientists, I mean, a lot of them will go into machine learning, and that's a good thing because we have a lot of things to develop there, basically. But it's also a bad thing because they will also kind of be missed in the physical modeling, and we will still need the physical model and we'll still need to continue to develop it. So I think there's a bit of a risk that we can divert too much of our attention right now to the machine learning models. I mean, we should definitely do that, but at the same time, we should also kind of keep the ability to run the physical models with the machine learning models in parallel.